Welcome everybody to our rapid fire panel discussion on opportunities and challenges for the future of data. My name is Joseph, I'm the policy lead at the IES, and I'll be facilitating the panel today. Today's event is part of the IES's Future of ES23 Horizon Scanning and Foresight project, where we're bringing together voices from across the environmental sciences through events like this one, with the goal of creating a vision statement that sets out the different potential futures for the environmental sciences, as well as how we can create the kind of future that we want to see. In that context, data is a fundamental part of the evidence base upon which environmental science is built. The past few decades have seen rapid developments in the world of data, significantly changing the landscape of how evidence is collected, curated, and used. Looking to the future, we can expect novel innovations and challenges for data, which will influence the future of the environmental sciences. For today's panel discussion, we have 4 expert speakers presenting on 4 topics around data, including case studies of best practice, novel ideas, and some challenges for the future. Each speaker will provide a short lightning presentation on a different topic linked to data, followed by some cross-discussion and chances for you to ask questions to some of the panelists. On our panel today, we have Ed Hill from the National Oceanography Centre, talking about the rise of infrastructure-level data collection. Michelle Walker from the Rivers Trust, presenting on citizen science as a key tool in the battle for healthy rivers. Martin Rogers from the British Antarctic Survey, who will address machine learning tools in environmental research. And Tom Reade from Hilson Moran, who will wrap up the presentations by discussing real-time environmental monitoring data and air quality. Thank you for logging in, and I'm going to now hand over to our panel of speakers, starting with Ed Hill. Professor Ed Hill, CBE, is Chief Executive of the National Oceanography Centre, NOC, one of the world's most innovative oceanographic institutions. He has a research background in physical oceanography, specializing in the circulation of continental shelf seas, and has participated in over 20 research expeditions. So Ed, over to you.
Thank you very much, Joseph. So what I wanted to do is contribute to this discussion with an illustration from the ocean realm, of how the mode of collection of data and the collection of data, basic data, is the foundation of all of the value chain of information in the environmental sciences. The picture here is an illustration of the Global Ocean Observing System, which is operated under a UN framework with multiple nations contributing different elements to it, ranging from fixed instrumentation through to drifting surface buoys, profiling floats, repeat ship observations, and so forth. The diagram looks fairly impressive. It looks like we've got the ocean covered. But in fact, there are many weaknesses in this. Some of these observations are actually only in the surface, not covering the deepest parts of the ocean. And crucially, some of these observations are very dependent on short-term project funding. And so although it looks like an infrastructure like is used for weather prediction, it is not anywhere near as resilient, funded really on short-term ad hoc funding. And so the real challenge in the ocean realm, but I think it's a challenge which applies in other areas of environmental sciences, is how we can transform systems like this. In ocean science, for example, it has been typical for researchers to have their own project, go out on a ship, collect their own data, bring it back, work it up, publish it, and then do that again. And the mode of doing ocean science is dramatically shifting, whereby that individual project, investigator-led collection mode of data is being not exactly replaced, but the balance is shifting towards scientists from across the world drawing their data, not on observations they have directly made themselves, but on infrastructures like this, where the data is generated by a distributed collection with multiple stakeholders contributing, and the data is being used for sciences. And therefore, it's an infrastructure-based model rather than a project-based model of data collection. So the next slide really just illustrates what I mean by a definition of an infrastructure. You know, it's a basic system with multiple users, which provides the bedrock for multiple activities. And some of the characteristics of infrastructure are listed in the blue box here. They typically have got high capital costs, a high proportion of fixed operating costs. They're not like projects which you can switch on and off. They're expected to last for a long duration. And they are very often free at the point of use. Just think of our transport network, the roads, they're free at the point of use, mostly. But somewhere the cost of them is being borne through some method of funding infrastructure. You're not paying each time you make a road journey, which is like a more project-based thing. It's funded through general taxation through an infrastructure model. There are other areas of science where the collection of data depends on big infrastructures, and there's some examples here from high energy physics and space science as well. And these are massive infrastructures in which there's high level, in these cases, international governance, and sometimes binding treaties or conventions which underpin the ways in which these are operated by multiple nations or multiple institutions over time. So actually today and for some time, we have been using various kinds of infrastructure for basic types of data collection. Often we use commercial ships where the capital investment in the ship already exists, and we pay a marginal cost to, for example, get the ship to carry scientific sensors for particular activities. And these opportunities are increasing, and indeed being expanded to citizen-owned vessels, and we'll hear more about citizen science later. And so some of the challenges here is actually the infrastructure, which is very expensive, such as a container vessel, is already paid, but there is then a marginal cost of how to use that, maybe to put a sensor on, and how do we find that additional cost. So this is one example of an element of the Global Ocean Observing System, the Argo Float Profiling Network, which is an example of an infrastructure. So the last slide then really just summarizes some of the issues that we are moving to, really trying to conceptualize some of the scientific data needs as actually no longer being project-based, but being dependent on large infrastructures with multiple stakeholders, often linked to international agreements. And crucially, trying to find funding models and business models which are suitable for supporting an infrastructure of the kind that I've described, that provides the basic data that is needed, and to move away from short-term project models. The other thing that needs to happen in science communities that are moving from project-based data collection to more infrastructural-based is there's a whole cultural dimension to the change, the way in which we do science, and different skills, and a huge amount of support and funding models required to move to that model. So I think this is part of the transition that we're moving in some areas, and indeed many areas of environmental sciences as we move into the future. So thank you, Joseph, and I'll conclude there.
Thank you, Ed, for what was a great presentation. And I think you gave us an excellent insight into the challenge ahead of us for transforming our data systems, courtesy of that really useful case study of ocean observing. And I'm sure that context of infrastructure is something which many people on the call will have their own examples of. So maybe we'll hear from some of them about their experience in the Q&A later. But it's my understanding, Ed, that you now need to sign off. So thank you so much for joining us and for that great presentation. But as we continue, not losing pace, our next speaker is Michelle Walker. Michelle Walker is Technical Director at the Rivers Trust, leading a team which provides innovative ways of using data and evidence to help understand river environments and deliver river improvements. In particular, she's leading on the River Trust's citizen science projects and work against sewage pollution. So Michelle, over to you.
Thank you very much, Joseph, and hello everyone, and thanks for having me. So the Rivers Trust is an umbrella body which represents about 65 and growing member trusts who are all concerned with really trying to restore and protect our rivers. And I'm going to talk to you a bit today about how we use citizen science, and also a transformational change project that we're embarking on to really try and make a huge difference in the impact that citizen science can have in our work. Yeah, so our rivers are in a serious state. They really are in a pretty poor way, and I'm sure Even if you don't work in a related field, you will have read and heard about some of the issues in the media. It's really growing in the public awareness. Only 14% of our rivers in the UK are in good ecological health, and none of them are in good chemical health. They're all chemically polluted, and really so many of them are suffering a staggering loss of wildlife and habitat destruction. And we've really shifted our baseline about what a normal healthy river should look like. I think it's quite hard to find a good example these days. So it's really about looking at what we can do to restore what we've got. In order to do this, we really need data and evidence that can help us tackle these problems, to at least understand, what is the current state of health. But that evidence is very thin on the ground. The map here shows the Team catchment, which is in the headwaters of the River Severn. The grey areas are water bodies where the Environment Agency collected no water quality data for a whole year. And this is, just a snapshot. It's something we see replicated across the country. The evidence base is getting thinner and thinner and declining. And, those budget cuts and the sort of declining government investment is really underpinning a lot of the problems that we're seeing, because we need that data to target action and to measure improvements. And it's critical that we have that for securing funding. And that means we need certainty on which economic sectors and activities we need to change first. And that chart on the right-hand side shows how certain the Environment Agency is about the causes of poor health in England's rivers. And as you can see, there's a lot of room for improvement there. Some of the solutions that we in the Rivers Trust movement advocate for are nature-based solutions. So things that you can do upstream in a catchment across a wide area of land, not just in the river channel itself. So things like river restoration, soil management, wetland restoration and creation, and tree planting. These can all fix many of those problems that we see, but also deliver many other wider benefits for nature and society. But quantifying those benefits is essential in order to secure the investment. And we are starting to work with industry, with green finance and insurers for things like investing in natural flood management measures. But to do this at the scale that we need, we've got to have much better data and evidence about the effectiveness of those measures, so that we can feed that into the decision support tools and the models that are used widely in those industries. So that's where we sort of come in, really, as the Rivers Trust movement. We work as a grassroots movement. We are very much based in communities and working with and for the sort of people that are members of the Rivers Trust. And those people across the country are often in the right place and the right time to be the eyes and ears on the ground to gather valuable data and information. And we've got really good citizen science schemes across the country, not just the Rivers Trust movement, but wildlife trusts and many other NGOs are using citizen science as a fantastic tool to fill information gaps. And that can be in a whole range of different thematic areas, including monitoring and surveying habitats and wildlife, water quality, pollution and issues, and gaining a picture of the health of the wider river catchment. And we've got some great examples from our member trusts and catchment partnerships where they are combining this citizen science information with their own professionally gathered data and evidence to give a really good sort of locally rich picture of what's going on. But that's not consistent across the country. We've got a really fragmented landscape of lots of different citizen science schemes and data platforms and apps and maps. And it's very challenging to combine all of that data together into an easily digestible format that we can put in the hands of decision makers and investors. And it's also hard to know whether all of those different types of data are trustworthy. A lot of schemes don't have quality assurance protocols. And this all undermines the ability to find sustainable funding to underpin doing more with citizen science. So that is where our CASTCO project comes in. So CASTCO stands for Catchment Systems Thinking Cooperative. It's a bit of a mouthful. It's an Ofwat innovation funded collaborative project. It's running for 3 years. We've got 24 partners on the project, including 12 water companies. We've got government, we've got academia, we've got NGOs. And we are aiming to develop, through co-design and collaboration, a national standardized framework for citizen science, and developing the training and the support and the data platforms and data integration tools to go with that, so that we can combine citizen science data with other tiers of information, things that you were hearing about from Ed there, sort of infrastructure, network of sensors, remote sensing, environmental DNA, all of those tiers of information combining together into a weight of evidence approach. And currently, we are going to be testing that out in 8 demonstrator catchments across England and Wales, and looking then to roll this out over the long term. So it's a 3-year project, but we want to make a transformational change, and we've set a long-term 10-year vision. So we're going to be looking to bring in additional funding to grow that and embed it. And really, it's about more than just getting good data to drive environmental change. It's about looking at the other pathways to impact that citizen science can enable. So things like increasing political advocacy and social sort of action and community-based action that can really spring out of people becoming more informed about what's going on in their local environment. And also individual behaviour change, you know, looking after our own footprint as well. So all of these things we're hoping to measure and really leverage over the next few years. And it's about as well giving back to communities, so providing the sort of health and well-being benefits of getting people out in nature, and improving skills and jobs prospects along the way as well through training. And you know, this is really our sort of core statement, really, that we're kind of driven by, is the change comes from the grassroots, it comes from communities, and we've seen huge power in putting data and evidence in people's hands. And this project will be about harnessing that and really organising it and getting a better collaborative understanding of river health so we can drive real change. Thank you very much.
Well, thank you, Michelle. I think that was a great presentation. And I think in particular that your transformational change approach via Casco was really interesting. And I think that it might already be the start of a theme for the afternoon as we look at data transformation with the goal of environmental transformation. And I think you also made a really strong case there for the role of partnership, and particularly citizen science, in the context of a data constrained landscape. So as long as we can address some of those challenges for bringing together the data. Next, we're going to hear from Martin Rogers. Martin Rogers is a machine learning researcher in the British Antarctic Survey, BAS, Artificial Intelligence Lab, and leads its Artificial Intelligence for Environmental Imagery group. Martin completed his PhD in machine learning and coastal science at the University of Cambridge, and previously worked at the Environment Agency and the National Farmers Union. So Martin, over to you.
Thank you for the introduction. I'm Martin Rogers, and I'm in the Artificial Intelligence Lab at the British Antarctic Survey. British Antarctic Survey, or BAS, is an interdisciplinary research institution. We do work, crucially, not just in Antarctica, but in both polar regions and more generally within the cryosphere, all to do with understanding how our polar regions are changing and how that could impact on the globe as a whole. And before I get into detail about the specifics of environmental applications, I know this is a talk about or a session about data, but I just wanted to talk about what artificial intelligence is, because it's a key part of how we are using that data. And I think it's just easily explained by looking at some of the examples that now exist in everyday life, or will invariably become everyday life in the near future. So driverless cars, Alexa or Siri, predictive text, traffic predictions, and ChatGPT, which has recently come off the ground. And what we are doing in the BAS AI lab is using these tools and techniques and algorithms that have been developed in different domains for different, primarily non-environmental reasons, and applying them to environmental questions. And so some of the environmental questions that we are trying to answer in the BAS Artificial Intelligence Lab using AI techniques includes the use of the techniques used for facial recognition and driverless cars to automatically detect sea ice or icebergs within satellite imagery. Things very similar to Google Route Planner is being used for the route planner of the Sir David Attenborough research vessel, which is our own research vessel as it navigates through polar ice-covered waters. We also use computer vision tasks for the likes of identifying wildlife from space, so albatross or whales or other major keystone species that are important to monitor and to continue to count their abundance of. And there are a number of other examples in terms of trying to identify the best place to put a new sensor, because there's only so many places in the world that we can, or even in Antarctica, that we can place a sensor because of its cost and remoteness, and also forecasting into the future. And so we've got an example down here, which I'll talk about in a minute, of IceNet. So trying to predict where sea ice extent will be in 1 month, 5 months, 10 months time. And in terms of some of the data that is available to us for this, well, we do have the ability to use some in situ data, so collared data, for example, on main animal species, and we also use a lot of reanalysis data, so data that has been generated from computational models. We can use that to aid our understanding of what has happened in the past to forecast the future, but we very heavily use a lot of satellite data. And so on the left here, we have an example of a passive microwave image. So passive microwave imagery captures sea ice extent every single day across the whole of Antarctica, but it is pretty coarse, only sort of 25-kilometer resolution. And then we have finer resolution optical imagery in the middle here, just to get your eye in. The red is sea ice and the black is open water. But the issue you have there obviously is cloud cover, which means often it is not possible to analyze that imagery. And on the right hand side, this is called synthetic aperture radar imagery, just radar imagery, and it has finer resolution again, but the issue you commonly have there is that it is not captured every single day, so you have an issue there in terms of its temporal coverage. So one way in which we've been using AI is to try and say, okay, well, we have this limitation in the optical imagery, as in this image A, where if it is cloud free, then it is pretty handy to see exactly where sea ice extent is, and to see other in-ice features such as leads or so on. But when cloud occludes the image, it's not possible to analyze it. And then you have in B here, this is an example of a radar image, where you have limited coverage temporally, as I've already said, and you also often have issues in terms of a lot of speckle, which makes it harder to immediately interpret what's going on in the image. And this is an example here of 3 images where we have applied a artificial intelligence tool trained on both image types. And if you look in the blue box that I have drawn here, then what you can see is that where you have both image types available, it outperforms the model which is trained only on optical imagery. As you can see in the optical imagery, there's a lot of blues and a lot of purples and pinks, which means it wasn't very sure when it was making its prediction as to whether it was ice or water. Whereas where we have both image types available, there's a lot of black and yellow, which means it was confident that this area is ice and the black areas were water. And that is because quite clearly it is being able to detect information that was in the corresponding radar image. So this is an example of using multiple image sources and us being able to gain more information than we would be otherwise using one image type in isolation. And then I talked about the passive microwave imagery. A lot of people really love this kind of video that I'm showing here. So passive microwave imagery has been captured for the last 40 years over Antarctica and the Arctic. And I really like it. I think it sort of shows in white the sea ice extent and almost sort of the heartbeat of Antarctica. And so what Tom Anderson, a member of our lab, has done is to take this 40 years of sea ice extent information that we have, as well as lots of other information pertaining to climate condition, oceanic conditions, atmospheric conditions, and so on, to try and forecast where sea ice extent will be in 1 month, 2 months, 4 months time. And you can see at the bottom here this bottom right, we've got the predicted sea ice extent in green and the actual sea ice extent in black. This is for 2012, so in the past. So we're predicting in the past to see how well it performs. And as you can see, with a 1 month lead time, we're resolving the sea ice extent with very high fidelity. As you can see, the performance then goes down as the lead time increases, i.e. the length of time between the last observation being made and then when the point at which we make the next prediction, i.e. 4 months in the future. But you can see that there's real promise here going forwards. Another example of where we're using this sort of passive microwave data and combining it here with collar data. So this is collar data of caribou that are crossing the Coronation Gulf in the Arctic Canada. And this is pretty neat, where we've been looking at what the relationship is between the date at which these caribou cross from this island, Victoria Island, back onto the Canadian mainland in the south. And as you can see, as it turns yellow, as the sea ice concentration starts to increase, then you can see that there is a few moments where you suddenly get these waves of caribou that start to cross because the sea ice conditions become favorable for them to do so. So this is work that we're now looking at in terms of doing the sea ice forecasts to try and predict when caribou may cross in the future, so that there can be a warning system for boat users and Inuit communities in the area to try and limit their activities at these times. And finally, another example of where we're trying to combine all this work together is in devising route plans for the Sir David Attenborough research vessel. And so we've got an example here that the kind of straight line, if you like, would be if you were completely if you had no information available to you about sea ice concentration and currents and so on, how you might go from this point up near the Antarctic Peninsula, quite near the Falkland Islands, down to our Halley research vessel, whereas actually in reality, you would take a route that stays a lot further north and then comes down the coastline, and that's due to the sea ice conditions that are present. So it's this work that's going on, generating these meshes of sea ice concentration, which are these red and white boxes, as well as meshes on current and on temperature and waves and so on, that can help us to optimize route planning in the area and to minimize fuel use, and also maximize the number of different locations that the research vessel can reach within any Antarctic campaign. Okay, thank you very much.
Thank you, Martin. That was a really interesting presentation. I think it was fascinating to hear about all the different angles to the role of AI and computation in the research, particularly as it goes beyond the monitoring into that forecasting role, and then hearing about something like the multi-image source approach or even the SDA route planning at the end there really does indicate the extent to which some of these historic challenges for data collection or monitoring that we would have once thought were insurmountable are actually something we begin to find ways around with some of this advanced computation and technology. Our final panelist is going to be Tom Reade. Tom Reade is an associate air quality consultant at Hilson Moran, an interdisciplinary building engineering consultancy. Tom has an extensive background in local air quality, having been involved in the industry for over 11 years. So Tom, over to you.
So briefly, I'm just going to talk about some of the developments in real-time environmental data collection, the importance of it, some case studies, and some of the challenges that we have, primarily around air quality data, but also the applicability of that sort of hypothesis against other environmental data as well. So firstly, in terms of the developments that we've seen in sort of the air quality field and environmental data has been largely due to the increased frequency of sort of air pollution events that have occurred. There is a significant increase in the awareness now from the general public, and there's obviously been a sort of a wider exponential growth in the number of air quality monitoring stations that have been installed, both from a national government level across the UK, the globe as well, but also on a local scale, which obviously brings in sort of that local and hyper local air quality monitoring, which has started to come forward as well. I mean, a good example of this is the Camden Clean Air monitoring network, which is a hyper local monitoring network which has over 200 monitors. They're spread out along all of the sort of the roads within Camden, sort of 200 meters apart. So it's quite an interesting and quite an interesting approach to collecting data, and one that's relatively new in the air quality field. Other developments that have led from in the air quality side of things is COVID-19 pandemic. There's been obviously a lot of work done as to the implications of COVID-19 on air quality, and a lot of analysis of the data that COVID-19 and the sort of the changes in traffic had on local air quality. But also there's been a sort of a consideration in terms of exposure. People are more aware of their exposure to air quality and other environmental considerations as well. And finally, health and well-being from an indoor environmental perspective. So obviously focusing on air quality as well, but also wider considerations around thermal comfort and daylight as well. It's also quite important to holistically consider all of those in one go, and how the collection of real-time data can be applied through digital forecasting, to give indications of how those indoor environments would perform in the urban environment. Looking forward now at the importance of environmental data, the key thing is increasing the evidence base. I mean, to be able to quantify, mitigate the impacts that we as humans have on the environment. So myself and probably a lot of other consultants and other people are undertaking extensive air quality monitoring, both indoors and externally, alongside the wider networks that are provided by government and local authorities. And it's key to understand that data and how that data feeds into the impacts that we're having and what is causing those impacts, and how we can mitigate and what changes we can make to mitigate those impacts. Accountability is also very important in terms of the environmental data that we're collecting. More recently, with the sort of the wider emergence of ESG, obviously on the E side, and the social side is how we measure performance against certain criteria, whether that be air quality objectives or whether that be any building accreditations that developments may have achieved, so things like the WELL accreditation or BREEAM, monitoring those indoor air quality parameters and comparing them against that. Thirdly, obviously the evidence base supports national and local policy development. So nationally, you could be looking at things like the air quality strategy, or on a more local basis, it could be air quality plans, and obviously the data that's collected through the monitoring networks to support any measures of improving local air quality, such as low emission zones and so forth. And finally, the data, real-time data can be used to assist in digital forecasting, as I've already mentioned. So that can help design the design development of the urban environments that we're looking at today. So we use a tool called the Healthy Cities digital forecasting tool at Hilson Moran. We also have one for healthy buildings, and it takes a wide range of real-time data that's collected across other buildings from other clients that we've been involved with, and obviously our own offices as well. We collect the information and we implement things like noise information, air quality, thermal comfort and temperature information into the tool, and that can be applied, and you can look at sort of floor plan by floor plan for the building side of things. On the city side of things, we take real-time information, so traffic data that's available from the UK's of the Department for Transport, real-time air quality information, and we also put that into sort of a healthy cities tool, which has enabled us to assess sort of the impact of that data and any upcoming development, on those environmental considerations. I'm just going to cover a couple of case studies now on some projects that we've worked on where real-time data has sort of influenced the approach that's been taken. So the first one was a project that we're involved in with RSSB, which is the Rail Safety Standards Board, and this was to consider the air quality implications of the operation of rail depots. So we looked at a number of depot types, so intermodal, which is bulk and passenger and freight, and ultimately the purpose of the study was to build on the evidence base, because at this stage there was very little evidence about the implications on local air quality beyond the depot boundary that these sites were having. It involved quite extensive collaboration with multiple different train operators and third-party stakeholders, and in order to get a feel of what we were looking at, we had to implement quite a large scale air quality monitoring survey across all the depot types, and that real-time information that we used supported the air quality modelling and the wider source apportionment study that was undertaken for each of the depots. We covered 6 depots in total across the whole of the network. And as I said, there were a variety of different uses. The reports are available through RSSB's website there. It was quite an extensive study, so it's quite a long report, but it's very useful in seeing how the application of the monitoring data was imposed into the source apportionment and modelling to determine some of the outcomes and some of the potential mitigation that could be in place to minimise the emissions from these depots on the public beyond those boundaries. The second case study is a project that I was involved in through Innovate UK and the Energy Systems Catapult. It was called Innovating for Clean Air. And the purpose of this project was effectively to assess air quality in a number of Indian cities and to effectively test air quality interventions to understand how we could look to support them in improving local air quality. And the key to this project was that the application of real-time air quality monitoring was effectively the key test bed for this. So a number of static and mobile monitoring devices are implemented. And the outcomes of this was that we were able to create a local air quality mapping tool through GIS and the data that was collected, so the public effectively could make more informed decisions and route decisions on their destination based on air pollution. As part of this, there was a number of Indian partners, sort of including the Indian government, local government, and some of the education universities out in Bangalore, where this testbed was implemented. The project is still ongoing. It's onto its sort of latter phases now, but again, it's developed into something significantly more in depth than I think was ever anticipated, and I think that's all come from this initial test bed, which, as I said, was air quality monitoring based, but has sort of transposed now into the application of electric vehicles and bikes and things like that, and the implication that has on local air quality as well. Just to finish now, just to cover some of the challenges, I think, which is probably the key thing really around environmental data, in particular for air quality. There are a huge amount of sensors available, and accuracy and precision is one of the key factors that would need to be considered. A number of these monitors are not particularly accurate, but also there are a number that are very accurate, obviously, but obviously these each all have varying cost implications as I come on to the next point. Like with all things, data collected, in particular air quality, there are vast amounts of it. Data is often recorded down to the minute, or it can be even recorded sub-minute. So if you're talking a year's worth of data, that's a lot of minutes worth of data in which needs to be analysed and reviewed. So one of the challenges, I think, will be in how that data is managed, selecting the appropriate data analytics tool to get the best out of the data that's being collected, and obviously that will largely be based upon what each person or each company or individual business wants to see from the information that they're collecting. One of the other challenges, I think, as has been previously mentioned, is that cross-collaboration and data sharing. At the moment, a lot of information is publicly available for air quality. However, there's also a lot of information, in particular in the built environment, from indoor air quality, where it's housed and kept hold of by the relevant companies or the tenants and so forth of those. What would be very useful, I think, in sort of building that evidence base would be to have that central point where everybody can feed in and understand what's doing, what's working, what isn't working. And I think finally, one of the challenges will be to use the air quality monitoring data to instill behavioural change. We've seen this slowly start to come forward in the Camden project, and also obviously the Innovating for Clean Air is about using that real-time air quality monitoring data to imply and to instill or try and instill behavioural change in sort of routes that people might want to take from destination, or encouraging not using vehicles and things like that. So there's probably more challenges at the moment than we've seen, but it's good. It shows that there's progress in this section. And that's pretty much it, I think, for myself. So thank you.
An excellent presentation again, and I think you made a great case for the importance of real-time data, and it was really interesting to hear about the role of monitoring networks in supporting those policy objectives, as well as sort of the human health angle to that. And in that context, I think the healthy cities and healthy buildings forecasting tools that you described sound like excellent resources. So it was really interesting to hear how real-time data can facilitate something like that existing. Now that we've heard from our speakers on the first go round, we'll be bringing back Michelle, Martin, and Tom to answer your questions. And we're going to start actually with a question that comes from Noel. And I think, Tom, will send this straight back to you to start us off with. The question is, although we have new data integration tools that will enable more to be discovered from the data we've already collected, often data is not freely available. How can we make data more easily accessible? So maybe starting with you, Tom, there's a lot of data coming out now around air quality that's useful, but some of it might be proprietary or might be inaccessible to people. So I wonder if you have any initial thoughts on that, and then maybe we'll see if anybody else wants to come in.
Yeah, absolutely. I mean, for air quality data, obviously there is a huge amount of publicly available information, whether that's from the UK government or each country's government as required, local authorities, or even individual monitoring by by building owners and things like that. But what isn't available is that very granular data on that building by building basis, which I think would be very useful in sort of taking our current available data to the next level. We see quite overarching data sets, we say, for air quality. So and it's quite sporadic in terms of its implementation where those are monitored. What we don't have is huge amounts of data points in close proximity, which give us that very, very true real life picture. As obviously the Camden example, the Clean Air Camden is one that is looking to do that on that sort of hyperlocal sort of approach, and it would be very useful for that sort of information to be more widely implemented and widely available. I know there are other test beds across the UK where this has happened, but yeah, I do think there is definitely a gap in the market for making more detailed and more hyperlocal information available.
Absolutely, and that hyperlocality is definitely something we're seeing emerging now, particularly in air quality, is something very desirable.
Yeah, I mean, it's something we're really concerned about. I mean, I've worked for the Rivers Trust for 12 years, and back when I first started, we could barely get information out of the Environment Agency on the current sort of ecological assessments. Now, you know, we've written so many letters and put so much pressure on government and politicians, and you know, we've seen a huge kind of advent of open data within government, but we're not yet there with a lot of the other data providers. I mean, we've just been writing to Water UK about the new requirements on the water industry to have real-time monitoring of CSOs, combined sewer overflows and water bodies, and just really sort of reiterating the case for open data and open standards and APIs so that data can be fully integrated together. And you know, I don't think there's a shortcut to doing it, but certainly keeping the pressure on and keeping the campaigning voice behind the need for transparency and open data, particularly for the water industry, which has a major public trust issue now. You know, it's finding those levers and trying to build the trust in that open data doesn't mean, you know, that it's a free-for-all. It's about improving the way that data and evidence can be used and combined with other data sets, you know, that tiered framework we were talking about. So it's trying to find the sort of win-wins, but also, you know, working through things like the environmental information regs, which we fall back on as well, which is really critical. And, you know, let's hope we don't lose that post-Brexit.
Thank you. And I think you actually just touched upon something that's come up in another question. So I think I'll put this straight back to you directly, Michelle, and then we'll move on to another area of questions and maybe bring Martin in. Dan asks about this specific point you've raised about combining data as a challenge, particularly the potential solution you flagged halfway through your answer about standards. Dan asks what would compel data creators or providers to adopt these kinds of standards for delivering data that can be used by the widest possible range of end users.
I mean, that is what we are battling with this Cascade project at the moment. So it's a bit of carrot and it's a bit of stick. You know, we can see that if we can get a sort of funnel of data and evidence underpinning the big investment from, you know, green finance, for example, that is going to fund nature-based solutions, they're going to be the pull for that data and evidence. And so you know, not only can we fund it better, but we can also write that into contracts. It's having a mandate and it's having funding, really. That's what it boils down to. You know, we've been trying for years to sort of tweak around the edges and get people, you know, agreeing to standards here, and everyone wants to sort of invent something new because they have control of it. We're trying to do really ambitious collaboration with this project, and it is hard and difficult and it's terrifying, but it's the only way you can do it. And trying to sort of have that end goal of driving it through the mandate of contracts and funding, I think, is the only way that we can see it's going to work.
Thank you. I'd like to stick on this theme of data robustness and validity for this next question, which is coming to you, Martin. I think you gave us a really good insight into how AI, machine learning, the benefits of good practice in that regard. But I wonder if you have any reflections on some of the risks and challenges involved as that evolves over the next 50 years, and if there might be any challenges around the robustness of data, the validity of data, or anything like that.
Yeah, so I just wanted to touch on one point to do with the last question, which I think is all to do with the importance of metadata. And I think particularly within the like satellite technology world, I guess because there are a lower number of providers providing huge amounts of data, there is increasingly consistency there and standards about the quality of metadata there, which then means it is more plausible if you're looking for concurrent data sources or data sources that overlap spatially, to be able to do that. And I think that there is increasingly a need not just to make data open source and freely available, but for there to be the supporting metadata there that you can actually search for it, and that you know, then it becomes far more accessible. To do with the risks going forward in AI or machine learning as a subset of AI, then that quality of data is, as you said, one of the big issues. Is not just the uncertainty that inherently comes from the data in the first instance, but it's also to do with the uncertainty that derives from the machine learning tool or the AI tool that has been developed. And in a lot of circumstances, you have tools where they won't, at the same time as producing their results, they won't also include information about their uncertainty when making those forecasts or making those detections. So I think that that's going to be a really important thing going forwards, that there are standards pertaining to how you inform a secondary user of this data that is derived from an AI technique about the inherent uncertainty and the sources in it. Yeah, that ultimately is very parallel to the point about the data access and data quality.
Thank you. And we've actually got a similar theme in this question. It's addressed directly to Tom, but perhaps is something that others might have a perspective on as well. And it follows that theme of analysis of data as a solution to reliability of data that arises from novel techniques, specifically about air quality sensors. So Canon asks, air quality sensor behavior can be very unpredictable. So how do you deal with the accuracy of real-time data generated from sensor-based technology? And do you use any AI techniques for air quality data analysis in that context?
So specifically on the AI element, we haven't yet branched out, I would say, into that aspect. I think the behavioural side of things in that sense is still relatively new. It's actually something we've been discussing as part of the Institute of Air Quality Management at the moment, about how behavioural and social elements will influence air quality in the future. But in terms of accuracy and precision of sensors, whether they're low cost or not so low cost sensors, typically the approach that we apply is to have those sensors co-located with a unit which is operated normally by DEFRA or somebody of that nature, which is typically sort of an AURN site, and effectively we compare the data sets and effectively apply and work out what the ratio difference is between those data. But obviously those co-locations need to happen relatively regularly and for a certain duration of time to ensure that you can have some confidence in the data that you're recording and you're presenting.
Thank you. Michelle, do you want to comment on that as well?
Yeah, we've actually just had an Alan Turing funded intern with the Rivers Trust for 7 months who was looking at using machine learning approaches to identify kind of errors in water quality sensors. and looking at, spotting sensors that have gone rogue and that kind of thing. So it's definitely something we are starting to explore through, the Casco project and our interest. And I think there's another question in there around, the capability to do big data analysis, and is something that having that intern embedded in our organizations really started to increase our data literacy, but has also identified that we have, huge skills and knowledge gaps in the NGO sector around this. And I think we've got to sort of look at growing it. And we've partnered with Data Camp, for example, to start increasing the training that we can share with our staff and with our members.
Thank you. And thank you for flagging up the question about skills for big data, because that's actually one I wanted to bring us to next, which is, do we think that the environmental profession and environmental scientists currently have the skills necessary to handle a world where big data is a much more prevalent concern? I wonder if maybe Tom or Martin, do either of you have any reflections on skills-specific challenges as we go forward?
I've just got one point where, I would say big data within reason, yes. Probably not the data sets that we're looking to develop in the future to give us that real-time environmental picture. I know we have recently engaged with a data analytics company to understand the application of data in a greater extent, more from a sustainability perspective, but the application of the environmental context would remain consistent, I think. So we are on that sort of that learning curve with them as to understand how the biggest, the big data sets can be applied from the information that we're getting.
And Martin, did you want to come in on that as well?
Yeah, I just wanted to say that environmental data is quite unique in the fact that often there are more problems with regards to its veracity, often missing data, so on and so forth. And actually, it doesn't really matter if you come from an environmental science background or if you come from a raw kind of computer science, engineering, mathematics background, whichever one you come from, this idea of handling environmental data tends to be something that people don't learn about in a lot of detail until post undergraduate level. And I think that's fine. I think it's important that people have a strong basis in one or the other, and then there are increasingly PhD programs or training courses, professional training courses that are set up that can help people to become specialists in that particular domain, i.e. the application and use of environmental data. And I think that in environmental science, there is more that can be done at that sort of undergraduate level or kind of professional courses about making people aware of the quality of data, missing data, veracity data, as I've already said, so that people are aware whether they actually do the analysis or are just users of the downstream data. But I think that we want to avoid this need that everyone tries to become specialists in environmental data and AI techniques and environmental science within one undergraduate course or so on, because it is too expansive for that.
I want to give everybody a chance at maybe one final sentence from each of the panelists, your takeaway from the event, where you think that an area of data or data as a whole might be going in the future. A final takeaway, and we'll go back down the panel in reverse order. So Tom, first to you, then to Martin, and then to Michelle. So Tom, any final takeaway from the event from you?
I just think we need to use the data that we have more efficiently and understand the data that we have and how that can sort of direct our future going forward.
Perfect, thank you. Martin, a final takeaway.
Yeah, it seems like the challenges we face are the same across different environmental domains. So learning across the environmental domains is very important.
Perfect. And Michelle, the final word goes to you.
Yeah, well, I think it's about empowering people and putting really good data and evidence in their hands. And, that's a challenge with big data, but I think we can do a lot by pairing up the experts with the people who can use the data and make a difference.
Perfect, thank you. That is all we've got time for. So thank you to Michelle, Martin and Tom for a great discussion, as well as to Ed, who had to slip out after his presentation earlier. Everything we've discussed today will help to inform our work throughout the year as we produce our vision statement for the future of the environmental sciences. If you'd like to be involved in those discussions, please get in touch and we can discuss how best to work together or integrate your perspective. Our Future of ES23 projects is still ongoing, and it's currently focusing in on the regulatory landscape, details of which you can find right now on the IES website. For now, that's it from us today. So thank you to everybody for logging in and participating, and I hope you found that beneficial and informative. Don't forget to record your attendance at this webinar in our CPD tool by logging into the IES members area if you're an IES member. And if you're watching the recording on YouTube, please do subscribe to the channel, like our video, and share it with your friends and colleagues. If you've enjoyed today's webinar, please do consider joining the IES as a member if you aren't already. But for now, thank you again to Ed, Michelle, Martin, and Tom. And thank you to everybody for attending and asking your questions. Hopefully, we'll see you again soon. Thank you.